Okay, I assume you've seen my previous video, which explains the new interpretation of our universe that must be used to explain unresolved issues with previous models. It is now time that I show you how this new theory solves these unresolved issues. You can see here the list of issues that we are going to talk about. So let's start with the first unresolved question, the Born rule. Although it's a bit technical, I'll use the simplest maths possible to focus on what is important. Let's take again the example of my previous video, where an atom is emitting a photon. While all particles are in fact field excitations, we'll use the particle level of description for our purpose. The problem is to determine the destination of this photon, more precisely, which atom will receive it. In our macroscopic world, we can usually determine fairly precisely the trajectory of an object. But at the quantum particle level, it is more tricky. We can only determine the probability of where the photon will land, so to speak. In quantum physics theory, there is a function that describes the state of a particle, in particular, its position, or its form momentum like for photons. When the photon leaves the atom, it is in a state psi0. And in our example, let's call psi1, psi2, psi3, and psi4 the states in which the photon could be upon next measurement. The current state psi0 can be expressed as a weighted sum of all possible next observations. And to calculate each probability to reach each receiving atom, the Born rule says it is equal to alpha1 squared to reach state psi1, alpha2 squared to reach state psi2, and so on. But why the square of the weight? Well, in our new theory, we need to take into account the responses of all the potential receivers, remember? And it actually makes sense because a probability is a percentage of chances which depends on all potential receivers. And for each potential actualization, the probability must be determined not only by the emitter state, but also by the receiver. So if we take these considerations into account, we need not only to apply the function describing the emission of the photon, but also the function describing the receiving atom's answer. That means multiplying the two functions, because we need both, not one or the other. And guess what? The maths tell us that the probability is equal to the square of each weight. So we can actually derive the Born rule instead of merely guessing it. We just need to take into account the potential receiver's responses. Okay, let's now look at the so-called measurement problem and the related wave function collapse syndrome. As seen in the previous video, the new theory I am using implies that all the interactions, such as the ones we've just seen, happen in what we called the quantum substratum. So all the interactions we just used to derive the Born rule actually happen in that domain. They do not happen in the space-time domain, where the final resulting events are the only events we can observe directly. Now, how can we use that interpretation to solve the wave function collapse and the measurement problems? Well, first let me remind you what these problems are about. In the standard quantum physics theory, everything happens in the space-time domain. So, if we take again the example of an atom emitting a photon towards another atom, we've seen that there is a function which describes the state of the photon traveling in space-time from the emitting atom towards, well, all the potential receiver atoms at the same time. In the standard theory, this is called the superposition of states. The photon actually seems to be in several places, or more precisely, to follow several trajectories at the same time. There is no other way to explain that function in the standard theory. This is weird, but what is even more troubling is that when the photon reaches its destination and we observe it, the function we just used to describe its state changes and becomes a new function that we must use to describe the photon state. It looks as if the fact that a result was observed created a change of the function. But at what moment did this change happen, and why? All of this has troubled physicists, at least the most curious ones, for over a century. It looks like magic is happening. Well, again, the solution to this magic situation is to drop the idea that everything happens in space-time. It actually happens in the quantum substratum. And suddenly, all the weirdness disappears. How so? Well, when the emitting atom is ready to emit a photon, it sends a so-called offering wave to all potential receivers, described by the same function as in the standard theory. All potential receivers will respond with a Hermitian conjugate confirmation wave, all of that happening in the quantum substratum. The products between the offering wave and each of the confirmation waves create, as we've seen before, probabilities which are used to determine stochastically the receiving atom. In other words, one among several possible choices is randomly made, a bit like in the spontaneous symmetry breaking of the Higgs field. And that is the actual measurement event which occurs and can be then observed in the spacetime domain. Thus, with this approach, and as far as spacetime is concerned, no need for a magic superposition of states, nor a function collapse enigma, nor a measurement problem, nor even a mysterious observer's action, which would happen in the spacetime domain. The observation we make in the spacetime domain actually happens just as a result of what really occurred in the quantum substratum domain. In the next video, we will see how non-local causality, entanglement, and the famous wave-particle duality can be explained with our new theory. See you soon!